Okay, so just now going through the examples on this stuff with mass defect and equals mc squared, we'll pick up with this one here. So consider 7 for beryllium, or beryllium 7, which has a mass of that, okay, and find the mass defect. So in other words, the difference between the mass when it is together as a nucleus and the mass of the nucleons that go into it when they are separated. So that is just, okay, and so the only really trick here is figuring out how many nucleons there are. So there are 7 total nucleons, 4 of them are protons. So that means there are 4 protons. And how many neutrons are there? Well, if there's 7 nucleons total, protons and neutrons, and there's 4 protons, that means there must be 3 neutrons. And we need to use this long one here because the question gave it to us, right? Don't just use the 1.67 from your formula sheet if you're given more significant digits. They don't just give you to that for fun. I got that the mass defect was that much. And that is unrounded, but it's also just actually to sig digs anyway, because we were given 5. All right, now to get the binding energy, well, that's the energy related to that much of a mass defect, because that's where the binding energy comes from, the difference in mass. And that's what I got. Now, how many atoms does this correspond to? Well, just one, right? So for every atom of this isotope of beryllium, that is the binding energy, right? So we could think of that as per atom. And as we discussed in the theory video, how do we then get it per nucleon? Well, we just found the total binding energy for the whole atom. Take that and divide it by how many nucleons there are. So that's our total binding energy, and we had 7 nucleons. So per nucleon, that is how much binding energy is required. All right. Now, what about binding energy per mole? Well, a mole is usually something we use in chemistry, and it's a lot of atoms because atoms are small. So if we're going to do something practical with them, we need a lot of them, right? So in just 1 mole, there are 6.02 times 10 to the 23 atoms. By the way, what's a mole? It's just the amount of something you would need to have its mass in grams be the same as 1 atom's mass in atomic mass units. So for example, to have 1 mole of hydrogen, since its atomic mass on average is 1.01, when you have 1 mole of hydrogen, you have 1.01 grams, and that works out to this many atoms. Okay, when you have 1 mole of carbon, you will have 12.01 grams of carbon, because that's the mass of 1 atom in atomic mass units. All right, anyway, so we have the binding energy per atom. We did that here, so let's find it per mole. So if we have that many per atom, well, now we just need to multiply it by the number of atoms in a mole. We get that. And now we're going to have to use 3 sig digs because this has 3 sig digs. So I got just 1 mole. You're looking at 3.43 times 10 to the power of 12 joules. 3.5 trillion joules of energy in just 1 mole. Okay, so you're looking at, so this is approaching like atomic bomb levels of energy. And I just realized for these ones, all my answers will still be right, except for sig digs, because I forgot that I used the speed of light here, 3.00, and that is a rounded value. So this is still what I would use for all my calculations that come after, but for my final recorded answer, I should say to 3 sig digs, because 3.00 times 10 to the 8. Same goes for this one. Okay, consider carbon-14 with its mass of that. Calculate its binding energy per nucleon. So nothing really too different here. To get the binding energy per nucleon, first you got to get the total binding energy. To get the total binding energy, you got to find the mass defect. So to get the mass of the nucleons, you got to figure out how many nucleons there are and what are there, right? So there's 14 nucleons total, and this is carbon. But uh-oh, they didn't give us the number of protons. Except they did, because carbon always has the same number of protons. So you go to your periodic table and you see that carbon has an atomic number of 6, and so it always has 6 protons. Which leaves, if there's 14 nucleons total and 6 of them are protons, that must mean 14 minus 6 is 8 neutrons. And I got the mass defect, the difference between the separate nucleons and the nucleus is that many kilograms. Okay, so now we've got the mass defect per atom. Let's find the binding energy per atom. Okay, so I got that many joules, and that's per atom, and every atom has 14 nucleons. So to get the binding energy per nucleon, take that, divide it by 14. And to 3 sig digs, because we did use the speed of light, which is 3.00, I got 1.18 times 10 to the negative 12 joules. Okay, the bomb dropped on Hiroshima was estimated as releasing 63 terajoules of energy. It flattened buildings in a 2.5-kilometer radius, destroyed about 70% of all buildings in the city, and killed an estimated 80,000 people immediately, with 50,000 more dying by the year's end. A pretty horrible application of the energy that is contained in just binding a nucleus together. Okay, so let's see how much mass it would actually take to produce 63 terajoules of energy. Tera means times 10 to the 12. And so I got 7.0 times 10 to the negative 4 kilograms, or if you'd rather, just 0.7 grams. So this is the mass that was converted to energy. It's not the mass of the bomb itself, but this is the amount of energy that can be released by just such a tiny amount of mass, right? It's kind of scary. It's almost something that when you think about applications like this, makes you feel like it's something we shouldn't have unlocked. Of course, this nuclear energy has a lot of great applications that we'll talk about later, but sometimes the good comes with bad. So it's a pretty incredible power that is contained in this binding energy. 0.7 grams, and it pretty much destroyed a city. Okay, just an example of working with atomic mass units here now. Remember, this conversion factor is on the back of your formula sheet. And 1 atomic mass unit is the same as... Right, so just another way of appreciating the fact that an electron is much smaller than a proton and a neutron, right? Protons and neutrons have atomic mass units of roughly 1, close to 1, right? Whereas an electron is 0.0005. Okay, if the binding energy of lithium-6 is 4.9118 times 10 to the negative 12, so that's this, what is the mass of the nucleus? So not the mass defect, the mass of the nucleus. So what should we do? Well, we have the binding energy, which can tell us the mass defect. We know the mass of that many protons and neutrons. If we have the mass of that many protons and neutrons, and we know the mass defect, well, then we can figure out the mass of the nucleus, right? Because the mass defect is just the difference between the mass of the neutron, the mass of the nucleons, and the mass of the nucleus. So that's our mass defect, which again just represents the difference between the mass of the free nucleons and when they're bound in the nucleus. So we can always figure out the mass of the free nucleons, right? Just multiply them by the mass. Now, they didn't give us the mass of a neutron and an atom here, so we can probably assume that we are safe to use 1.67 times 10 to the negative 27 kilograms for both. So in lithium-6, what does that 6 tell us? That tells us the number of nucleons, right? What does lithium tell us? The number of protons, because if you're lithium, you have 3 protons. Game over, end of story. Lithium can never have not 3 protons. So we have 3 times the mass of a proton. How many neutrons does it have? If it has 6 total nucleons and 3 of them are protons, it must have 3 neutrons. So I got that many kilograms, but be careful, read carefully. It asked for the mass of the nucleus in atomic mass units. So just take that and multiply by our conversion factor. 1 atomic mass unit is the same as 1.66 times 10 to the negative 27 kilograms. So I got, okay, and if you use the unrounded masses of protons and neutrons that they've been giving you, you would get, I think, 6.02 atomic mass units, but since they didn't give us those, we kind of assume they want us to just use the ones on the formula sheet. So if they give you the mass of a proton and neutron, use it. If they don't, use the one on your formula sheet. Okay, atomic mass is defined as being 1/12 of carbon-12. What is the mass of atomic mass unit? Is defined as being 1/12 of carbon-12. What is the mass of carbon in atomic mass units? So you can kind of just think of this as a definition. If 1 atomic mass unit is 1/12 the mass of carbon, well, by definition, carbon-12 has a mass of 12 atomic mass units, right? Or you could think of it this way. So just manipulating this then, the mass of carbon-12 equals 1 atomic mass unit times 12. Okay, the mass of an unknown noble gas is this. Which gas is it? Okay, so it's kind of weird what this is asking. It's saying it should really say the mass of an atom of an unknown noble gas. So remember, what does that atomic mass on the periodic table tell you? It tells you the atomic mass in atomic mass units, right? In chemistry, we say it's the grams per mole, but really that's just taking the atomic mass and blowing it up to the size of Avogadro's number. So if we can find that in atomic mass units, then we can compare it to the periodic table and figure out which noble gas this is. So, and you get that it's 83.7 atomic mass units. So it's not a perfect match for any of the noble gases, but krypton is 83.8. Remember, that's an average, right? This thing with an atomic mass of 83.7 atomic mass units could very well be an atom of krypton. You might be saying to yourself, well, how can it have 0.7 neutrons or protons? Careful, that's not exactly what atomic mass units means, right? Because remember, as you now know, some of that mass can disappear as energy. In fact, some of it does disappear as energy. So it doesn't mean that it has 0.7 of a proton or neutron. It means that together, the mass works out to 83.7 atomic mass units. It does have an integer number of protons and neutrons. They just don't have a mass of one atomic mass unit. The only time a proton and neutron have exactly the mass of one atomic mass unit is when they are in carbon-12. Every other time they have a slightly smaller, slightly larger mass, and we just decided to define it based on carbon-12. So by definition, they kind of have to have the mass of one atomic mass unit when they're in that nucleus. Okay, just some more examples with these kind of weird units here. Give the mass of an electron in mega electron volts per c squared. So first we need to find its energy equivalence. In other words, if the mass of an electron were entirely converted to energy, how much energy would you have? Okay, so you would have that much energy in joules. We need it in electron volts and then eventually mega electron volts. So we'll do 1 electron volt is the same as that many joules, and 1 mega electron volt is the same as this many electron volts. Make sure they cancel out correctly and that you haven't mixed up your ratios. Whoops, 10 to the 6. And there we go. We're left with mega electron volts, and that's what we wanted. And so we just put it back into this, except we don't actually divide by c squared. And like I said, if you ask a nuclear physicist for the mass of an electron, they will not say 9.11 times 10 to the negative 31 kilograms. They will say 0.512 mega electron volts per c squared. Because so often what's really important is the energy equivalence of a given mass, not the mass in kilograms. Okay, a particle has a mass of that. What particle is it? Ooh, okay, so how can we figure out what particle it is? Well, get the mass in kilograms, because all the ones on the back of your sheet are given in kilograms. Well, actually, that's a lie. They're all also given in electron volts and mega electron volts per c squared. So that's a good way to check our work here too, actually, right? Because on the back, you'll see that the mass is pretty close to this. Looks like a bit of a rounding issue somewhere, but they probably used a lot more sig digs than we did, so pretty good. But nothing there has 0.94, so we are going to have to find this in kilograms and, well, hope it's something on our formula sheet. So now we're given the energy equivalence form of the mass. So now we're given the energy equivalent. If we actually do the division by c squared, we will have just a plain old mass. But first, let's turn it to joules per c squared so that when we do that, we know we're getting kilograms out. So first, let's get electron volts. So there are 10 to the 9 electron volts in 1 giga electron volt. And then we want to get rid of electron volts and replace it with joules. And that should work. Let's check by canceling out. Giga electron volts with giga electron volts, and then electron volts with electron volts, and very good, we're left with joules. As long as we didn't mess up any of those conversion factors, we should be getting now a mass in joules per c squared. Notice how now this is just m equals e over c squared, right? We're just manipulating e equals mc squared to get m, which is what we wanted in kilograms. So I got the mass is 1.67 times 10 to the negative 27 kilograms. So that is either a proton or a neutron. We don't have enough sig digs here to say for sure. Okay, calculate the mass equivalence of a blue photon in kilograms and in EV per c squared. Okay, so how would you approach this? Pause the video, try it out. We have the wavelength of a photon, which means we can find its energy, right? And if we have an energy, we now know we can find the equivalent mass with E equals mc squared. So we kind of see a path forward, right? So first, let's find the E. We're given a wavelength, so we'll use this form of Planck's equation. So the energy of a blue photon is that many joules. Okay, if that much energy would be completely converted to mass, how much mass would it be converted to? Well, for that, we need Einstein's equation, right? So I got that if all of that energy were to be converted to mass, you would get that many kilograms. So not much. Okay, so it asks for it in kilograms, so we can do that to sig digs, and that's a 1 answer. But if we want it in electron volts per c squared, well, we have the energy. If we convert that to electron volts and divide it by c squared without actually dividing by c squared, we have the mass in terms of eV per c squared. So we have that many joules per c squared. We just need to turn those joules into EV and we'll be good. So make joules go away and be replaced with electron volts, and that's the conversion factor. So I got to 3 sig digs. That is the mass in electron volts per c squared. Okay, that wraps up the examples video. So topic 1 is for sure done. If you are looking for practice, try out the topic 1 practice assignment in the Google Classroom or Agenda.